Welcome back to AMETEK Brookfield University, and welcome to all our first-time viewers. In this module, we'll cover basic fluid rheology and data interpretation. We'll learn about shear stress, shear rate, how to calculate viscosity fluid behaviors, as well as how to process the data collected. Hi, I'm Mark Caholen from AMETEK Brookfield. So let's get started. Let's look at this fluid model. On the left, picture this as a stack of cards. There is a distance between the stationary plate and the top moving plate. This diagram represents the sample material in a container, where the container wall is the stationary plate and the spindle surface is the top movable plate. As the spindle is rotating at a fixed velocity, the sample in contact with the spindle is moving at that same velocity. As we move further away from the spindle, the velocity of the sample decreases until it is at a standstill at the container wall. This is known as a flow gradient. The spindle is applying a measurable force to the sample under these dynamic conditions. So what is shear rate? In this diagram, the stationary plate represents the container wall, and the moving plate is the spindle surface. The distance between the two plates, x, is measured in centimeters. The velocity of the spindle is measured in centimeters per second. Gamma dot represents shear rate in reciprocal seconds. Dividing the spindle velocity value in centimeters per second by the distance between the stationary and moving plates in centimeters, the resulting value is expressed as 1/seconds, or reciprocal seconds. This is the formula for shear rate. This assumes that the plate length is significantly greater than the distance between the plates. Since the spindle is always rotating, it appears to the sample to have infinite length. Now let's look at shear stress. Shear stress, or tau, is equal to the amount of force per unit area, or in the case of the viscometer, dynes per square centimeter. So shear stress will be displayed in dynes per square centimeter. We have already looked at shear rate. Gamma dot is equal to the velocity gradient. That gradient is determined by the spindle velocity and distance from the stationary wall of the container. So velocity in centimeters per second is divided by distance between spindle and container wall in centipoise. This results in the shear rate in reciprocal seconds of shear. What do we need to know to calculate viscosity? Viscosity equals the shear stress divided by shear rate. So eta equals shear stress in dynes per square centimeter divided by reciprocal seconds of shear. Eta is viscosity in poise. 1 poise equals 100 centipoise. When we talk about an AMETEK Brookfield viscometer, we're talking about dynamic or rotational viscosity. Viscosity units are reported in either millipascal seconds using the SI International System of Units, or in centipoise using the CGS or centimeter gram second system of units. The conversion from centipoise to millipascal second is 1:1, so both systems of units equal each other. Kinematic viscosity, on the other hand, is typically measured with a capillary tube or Zahn cup and is reported in either square millimeters per second using SI units or in centistokes using CGS units. Again, the conversion between the two is 1:1. There is a relationship between kinematic viscosity and dynamic viscosity. Converting from centistokes to centipoise is done by multiplying centistokes by the density of the fluid at the test temperature. It's important to note that this conversion is only valid when testing Newtonian fluids. Newtonian fluid viscosity is not affected by shear rate and remains stable over all shear rates. Mineral oil, water, honey, silicone, and glycerin are examples of Newtonian fluids. Non-Newtonian fluids can exhibit several types of behavior. Pseudoplastic materials have lower viscosities at higher shear rates. Hand lotions, inks, and shampoos are examples of shear thinning materials. Plastic fluids will not flow until their static yield stress value is exceeded. Once this stress value is exceeded, plastic fluids typically exhibit pseudoplastic behavior. Ketchup and mayonnaise exhibit pseudoplastic behavior. The viscosity of dilatant material will increase with increasing shear. Cornstarch, ceramic slurry, and cement are examples of materials with dilatant behavior. Thixotropic materials become less viscous over time at a constant shear rate. Paint is an example of a thixotropic material. Newtonian fluid viscosity is independent of shear rate. Any spring, spindle, and speed will have no impact on the viscosity of these fluids. When plotted with viscosity on the y-axis and shear rate or RPM on the x-axis, you can see that the viscosity remains the same with a varying shear rate. Remember that viscosity is equal to shear stress divided by shear rate. The graph on the right shows that as long as the relationship between shear stress versus shear rate remains constant, the viscosity will always remain the same. Non-Newtonian fluid viscosity is dependent upon shear rate and stress. The measured viscosity value is accurate only for the exact method parameters. This includes not only the 3S rule of same spindle, speed, and spring range, but also temperature, container shape, and sample handling and conditioning. With non-Newtonian fluids, the relationship between shear stress, or tau, and shear rate, or gamma dot, is not constant. Other non-Newtonian fluid viscosities are time-dependent. Thixotropic or rheopectic fluids will either become less or more viscous with time. Time-dependent non-Newtonian fluids can be shear thinning, shear thickening, or plastic in behavior, where liquid flow will only begin once the static yield stress is exceeded. Pseudoplastic or shear thinning materials will display lower viscosity as the shear rate is increased. The relationship between shear rate and shear stress does not remain constant. As the shear rate is increased, the shear stress begins to level off. Plastic fluids will act as a solid under static conditions. A certain amount of stress must be applied to the fluid before it begins to flow. This stress is called static stress. Once the static stress is exceeded, flow will begin. In this case, the fluid exhibits pseudoplastic behavior. You can see that when the material begins to flow, it is already at a higher shear rate than zero. As you can see on the graph, the fluid will not begin to flow until the applied shear stress exceeds the static yield value of the fluid. Once the value is exceeded and the flow begins, plastic fluids may display Newtonian, pseudoplastic, or dilatant flow characteristics. The opposite of pseudoplastic is dilatant. Here we see viscosity increasing with an increase in shear rate. In this case, as the shear rate increases, the shear stress rises disproportionately. Thixotropic fluids will undergo a decrease in viscosity with time when subjected to constant shear. Hair conditioner, lotions, and sunscreens are examples of thixotropic fluids. Rheopectic behavior is the exact opposite of thixotropic behavior. A fluid's viscosity will increase with time as it is sheared at a constant rate. Gypsum demonstrates rheopectic properties. Thixotropy can occur in any of the previous flow behaviors. Here we see a fluid with pseudoplastic behavior. A shear sweep was performed by increasing the shear rate and then returning down to the initial shear rate. Notice that the up curve and the down curve do not coincide. The final viscosity is lower than the starting viscosity. This difference is hysteresis and represents thixotropy. In some cases, this is irreversible, and in others, a rest period will restore viscosity to the original value. The corresponding graph shows that when the test is complete, the initial shear stress was higher than the final shear stress at the same starting shear rate. Again, rheopectic behavior is the opposite of thixotropic behavior. We see that after performing a shear sweep from low to high and then back to low, the final viscosity is higher than the initial viscosity. This indicates that shear thickening with time and shear has occurred. The graph shows that the final shear stress is higher as compared to the initial shear stress seen at the start of the test. Let's review the types of behavior we have just discussed. The purple line on the graph represents Newtonian behavior. The viscosity is independent of shear rate, and the ratio of shear stress to shear rate remains constant. Pseudoplastic behavior is seen as viscosity decreases with increasing shear rate. As the shear rate increases, the ratio of shear stress to shear rate is no longer constant. The shear stress begins to decrease with increasing shear. Dilatant fluids behave opposite of the pseudoplastic fluids. As the shear rate increases, so does the viscosity increase. The shear stress is no longer constant with the shear rate. As shear rate increases, the shear stress proportionally increases. Now you understand the basics of fluid rheology, including what is the shear stress and shear rate, how to calculate viscosity, and the different types of fluid behavior. With these principles in mind, we'll look at how to interpret data from various test methods. To define a fluid's rheological property, a shear sweep can be performed, profiling the rheological behavior of your sample. In this example, an RV range instrument was used with an RV3 spindle. Heavy-duty multi-seal was the reported sample. Optional AMETEK Brookfield RealCalc key software gathered and saved the data. A temperature bath controlled the sample temperature at 25 degrees C. 4 speeds were selected, ramping up from 1 RPM to 10 RPM, and then ramping back down to 1 RPM. This resulted in a 7-step program. Each step had an end condition of 30 seconds, with 1 data point taken at the end of each step. Torque values were recorded, as well as viscosity. As can be seen, this fluid exhibits pseudoplastic or shear thinning behavior. As the speed increases, the viscosity decreases. When we sweep back to the starting speed of 1 RPM, the viscosity returns to its initial value. Actual results show a starting viscosity of 33,800 centipoise and a final viscosity of 32,100 centipoise. Remember, instrument accuracy is 1% of the full-scale range. In this case, the full-scale range of an RV range instrument using the RV3 spindle at 1 RPM is 100,000 centipoise. 1% of the full-scale range is plus or minus 1,000 centipoise. So if we subtract 1,000 centipoise from 33,800 centipoise, we get 32,800 centipoise. If we add 1,000 centipoise to the final 32,100 centipoise, we get 33,100 centipoise. Based on the accuracy of the instrument, there is an overlap in the results of 700 centipoise. As long as there is any overlap in the viscosity values when taking into account the instrument's accuracy, we have to state that, based on the accuracy of the instrument, these two values are considered the same. This indicates the fluid has fully recovered its viscosity. When presented with data in this format, there's a faster way to determine whether the two viscosity values are within the accuracy of the instrument or are significantly different. We know that the instrument accuracy is plus or minus 1% of the full-scale range viscosity. Well, torque also follows the same rule. Torque readings are also accurate to plus or minus 1% torque. So if we look at the first torque reading of 33.8% and subtract 1%, we get 32.8% torque. If we add 1% torque to the final torque value of 32.1%, we get 33.1% torque. We can quickly see that there is an overlap of torque from 33.1% for the final value and 32.8% for the first torque value. When comparing two results based on the same speed, spindle, and spring range, the simple rule is if the torque values are within 2% of each other, they would be considered to be the same viscosity based on the accuracy of the instrument. Let's take a look at the data from the same fluid being tested on an LV range instrument. This visual amplifies the importance of creating a method that defines the type of spindle, speed, and spring range to be used for testing. In both cases, pseudoplastic materials will be shear sensitive, and choosing the shear rate for the method will have a significant effect on viscosity. If we look at the starting and final torque at 1.5 RPM using the LV range instrument, we see that there is a difference greater than 2%. Starting torque was 35.2% and the final torque was 32.8%. This is a significant measurable difference in viscosity. In the case of the LV test results, hysteresis was observed, and thixotropic behavior is noted. This may be a result of the longer test program, or perhaps the higher speeds resulted in some breakdown of the product viscosity. Here's a graphic representation of a rheogram. An AMETEK Brookfield DV3T HB range cone plate viscometer was used with a CPA 52 cone. The cone plate geometry has defined shear rates, which results in reporting shear rate and shear stress. Data shows 5 shear rates were run, ramping up and then back down. Each step had a runtime of 60 seconds. Let's look at the starting and ending torque values. There is almost a 10% difference in torque. Hysteresis has occurred during this test with a significant loss in viscosity over the duration of the test. This may indicate time-dependent thixotropic behavior. Again, this may be the result of time or breakdown of the fluid from shear. In either case, pseudoplastic behavior was observed. One way to determine if a permanent loss of fluid viscosity occurred is to let the material sit for several minutes and then begin the test again. If the viscosity goes back to the original value, then the fluid fully recovered. If the value is closer to the final viscosity value, then permanent loss in viscosity has occurred. Newtonian fluids behave in a very predictable way. Regardless of the shear rate, speed, or geometry used for testing, the results will always be the same. Here, the speed varied from 50 to 100 RPM, with corresponding viscosity values remaining stable at around 675 centipoise. We still recommend having a standard method for testing Newtonian materials to avoid any questions about varying test methods. As can be seen in this data, shear rate varies from the low of 17 reciprocal seconds to the high of 34 reciprocal seconds. Viscosity remains around 675 centipoise for all shear rates tested. This rheogram shows a material with pseudoplastic, time-independent behavior, and its viscosity fully recovers at the end of the test period. It's difficult to see the difference between the ramp-up and ramp-down data points since they are practically lay on top of each other. Each speed was run for 5 seconds before a data point was taken. Starting torque was 69.6% and final torque was 68.6%, well within the 1% accuracy of the instrument. So the opposite of pseudoplastic behavior is dilatant behavior, where a fluid's viscosity increases with increasing shear. A dilatant fluid can also be rheopectic behavior as well, where over time the material will thicken. In the graph, you can see that as the speed increases, the viscosity also increases. The initial and final data point at 20 RPM only has a 0.7% torque difference, indicating that these two values would be considered equal, indicating full recovery of fluid. As a reminder, when reviewing results, always look at the reported value. When the test conditions are known, take into consideration the accuracy of the results. We've talked about a quick comparison between results when looking at the torque value, but some results may only have viscosity reported. Knowing the test instrument's full-scale range based on the test method used allows you to calculate the accuracy of the results. The tolerance for viscosity variations can be set as high as 20%. Therefore, it's best to create a test method where the results fall somewhere in the middle of the instrument's torque range, allowing for wide variations in results to be measured within a torque range of 10 to 100%. In the next training module, we'll take into consideration the experimental parameters that need to be established for accurate test results. If you have any questions regarding this training module, call 508-946-6200 or visit brookfieldengineering.com. We'll gladly answer any questions you may have.